section 8.3 is where we take what we just talked about with binomial distributions, and now we start to try to do confidence intervals and then hypothesis tests with them. So in this section in particular, we're creating confidence intervals with binomial distributions. Now you just finished the previous problems, so you already know what binomial means. It all focuses on this word bi, but just as a reminder, binomial just means that there are only two possible outcomes. So this is something like heads versus tails if you're flipping a coin, or success versus failure if you're doing a research study, or yes versus no if you're voting on a political decision. So there are lots of these. By the way, there's one binomial probability or one binomial distribution that's really important right now, and it is those who have had the coronavirus and those who have not had the coronavirus. So there's the infection rate, or the proportion of the population that's gotten the virus yet. And that P here always stands for proportion of the population. And so it's important that we think about, we go back and we think about the big idea of doing confidence intervals to begin with. And that is that for confidence intervals, we're always trying to make sense of moving from our sample to our population. So we know some things about our sample, and we want to use those things about our sample to understand our population. So for example, in the past, we knew what X bar was. This is the word average. And then we wanted to take that to guess what mu was for the population. So these two words both mean the word average. Similarly, we had the words that meant standard deviation. And we know that from our sample, standard deviation was always S, and then when we get over to our population, standard deviation was sigma. Now we're going to talk about what we call a proportion. And for a proportion, when we're in our population, we'll always refer to the population just with the letter P. This is kind of unusual because this is an English letter. Usually our English letter is over here, but our English letter P is what we mean to say the proportion of the population. So for example, P is how many people in the United States have been infected with the coronavirus. It's the percentage, the proportion of people. P hat is our sample. So P hat is the people that you have studied that have been affected. So notice maybe you are working in some sort of town, and you say, hey, we've had a sample of 100 people come through the hospital. We've tested them, and we found that 30% have tested positive for coronavirus. That means your sample is at 30%. Does that mean the population is at 30%? Well, it could if those people were selected randomly. Then that means that this sample could be used to give a picture of the population. For those following along with the coronavirus, though, we know that that's actually a real problem with using the sample to understand the population, and it's that a lot of people who get it never get tested, and so they don't end up in the sample. The sample is not truly a random sample. But okay, don't let me get distracted talking about the coronavirus. I know that's not what you all are wanting to think about right now. You all would much rather think about statistics, I'm sure. Okay. So we're trying to move from our sample to our population, and this over here is what we call our point estimate. So all we mean by that is that this is the term that we use to guess what P is. But our point estimate, P hat, has a formula to it, and you can probably guess how we can calculate our point estimate, P hat. And that is, P hat is easily calculated as just the number of successes, or the number of however many things we're counting. So the number of successes in the coronavirus samples, the number of people who've successfully had coronavirus, number of successes divided by the number in the sample, so the total number of observations. So the book may write this slightly different, but it's just the number of successes in your sample divided by the total number in the sample. So you've studied 500 people, 200 of them have tested positive, so P hat is 200 divided by 500, and that gives us that picture. Okay, so what we want to do is we want to use these things to collect to create a confidence interval. So let's go back and remember, what did a confidence interval look like before? So previously, our confidence intervals looked kind of like this. We had X bar minus ZC times sigma over square root of n is less than mu is less than X bar plus ZC times sigma over square root of n. So this was our confidence interval. And what we're going to have today is something that's very similar. Notice we also had a second one with S's and T's, but they're basically the same formula. Today, whenever we're working with a binomial data, whenever we're working with a binomial distribution, our formula is going to be almost the same formula. We're just going to make a couple very small changes. And instead of x bar, we're going to use p hat. So instead of using our average, we're going to use the proportion. But notice the proportion is kind of like an average. It's the percent of successes that you have. We're still going to use a z distribution because we know that for binomial data, it really takes a really nice normal distribution after you do enough samples. Now, instead of our standard deviation over the square root of n, that's where we're going to make a change. And our change is going to look like this: p hat 1 minus p hat over n. Why is this the same as sigma? Well, if you remember from the previous class period, we talked about how to calculate the mean and standard deviation of a binomial distribution, and our mean was p times 1 minus p. Our standard deviation was mean times 1 minus p. So p times 1 minus p is our is how we calculate standard deviation. So it makes sense that that would replace sigma in our formula. One quick note: the book often uses the letter Q to mean 1 minus p, or Q hat to mean 1 minus p hat. So the book often uses this. So when you see Q written in the homework, when you see Q written in your notes, in your textbook, that's what it means. I'm not going to use it very much in my notes because it seems like it's not that hard to just write 1 minus. So I'm just going to write 1 minus. But when you see that, that's what it's getting at. Okay. Instead of mu, we're calculating the confidence interval for p, and then we have the exact same thing with a plus sign, just like we've always had for our confidence intervals. So plus zc times the square root of p hat 1 minus p hat over n. Sorry for the poor legibility here, but it's that again. Okay. So this is our confidence interval. There's a question we need to ask, and that question is, when are we allowed to use this estimate? And the answer is, you're allowed to use this estimate if two things are true. If n times p hat is greater than 0.05 and n times 1 minus p hat is greater than 0.05. So what's the real logic here? The logic is we're going to allow ourselves to use this test as long as we should expect to have at least 5%. Oh, no, it's not greater than 0.05. It's greater than the number 5. As long as it's big enough for us to expect to have 5 successes and at least 5 failures. So notice this is the number of successes, the probability of success, and this is the probability of a failure. So really, we're just saying, do we expect to have at least 5 successes and 5 failures? The reason for this is our confidence interval doesn't work really well when you start getting to these extreme cases where you have, like say, for example, you want to figure out what's the probability of winning the lottery, and you go and buy 100 lottery tickets, and you know what? None of them win. So does that mean the probability is 0? Well, it's not 0, but it's just barely bigger than 0. And so so if you want to start measuring probabilities that are really close to 0, you have to have a really large n before you can start making sense of that. In fact, your n needs to be large enough that you'd expect to have at least 5 yeses. So if you're studying lottery tickets, you need to buy enough of them that you have at least 5 successes. By the way, lottery tickets, we can do like a probability problem like from chapter 3, but that's not here nor there. You also need to have at least 5 failures. So that's when we use this estimate. It's not the biggest thing that we think about this semester, but it's always worth asking, am I actually allowed to do this, or am I just making stuff up? Hopefully you don't always feel like you're making stuff up. Okay, let's come and tackle the problem. So let's tackle problem 8.7 and see how we do something like this in practice. So in 8.7, we have 250 individuals and 40 of them approved. So what do we need to do? I need to come over here to this formula that we had earlier, our binomial formula, and let me erase our distracting parts. So we need to come over here and calculate this binomial part. So we need p hat. Notice we still have the same p hats in and zc. So all we really have to work out is what is p hat, what is n, and what is zc. Well, a couple of these are pretty obvious. In this one, we're doing a survey and we're saying, do you approve or disapprove of the way Congress is handling its job? By the way, the answer is always disapprove. Like almost everybody disapproves. Okay. We had 250 people respond and 40 said they disapprove. So this 250 people, this is our N. That's the number of people responded. So this is the total size of our sample. P hat is not the number that approve, it's the percent that approve. So P hat is 40 divided by 250. And so I'm going to divide this real quickly. I feel like I should be able to do this in my head, but it seems harder when the camera's on. Okay, and this is 0.16. And now ZC, how do we figure out ZC? Well, ZC comes from the fact that we're looking for a 90% confidence interval. Oh, maybe I should do this problem. Let's go ahead and start on part C, and then we'll come back. So we're looking for a 90% confidence interval. So that means I'm drawing my picture here. I have ZC here. I have negative ZC here. I want 90% in the middle. I also have 5% here. So I'm going to use inverse norm, and I'm going to use my area equal to 0.95. And then my standard deviation, my mu is going to be 0, and my sigma is going to be 1. So I'm going to put all that in my calculator and come out with my answer. And inverse norm, 0.95, and I get 1.64 for my ZC. This has happened enough that I feel like I should probably have this memorized by this point. Okay, so these are these things, but let's stop for a minute and just ask, how would I answer the actual questions that are on exercise 8.7? So the actual questions I would answer, the first one I would say, what is the point estimate P hat? Well, P hat is just that 40 over that 250, and so it is 0.16. So 16% or 0.16. So that means about 16% of people in this study said they liked Congress, which, by the way, is pretty much par for the course. It's pretty common number. Are we justified using a normal approximation? Well, let's say, what is N times P hat? Well, N times P hat is that 40 number, and that's a lot bigger than 5. So we definitely had at least 5 people approve. Furthermore, N times 1 minus P hat is going to be 210. So you could do 250 times 0.84. And notice that's also bigger than 5. So the answer is yes, because each of these numbers were quite big. You only get no if this proportion is so small that when you multiply by N, you don't have enough successes and enough failures. Okay, so now we're ready to get to the real thing that we're interested in, and that's part C. And so part C is where we start using our binomial formula. So part C, we're going to take this formula that we had right here. We're going to take this binomial formula, and we're going to try to write all the appropriate things on it. Okay, so part C will come, and we'll just put in our P hat, ZC, and all of our different pieces. And so that means we go 0.16 minus 1.64 square root 0.16. And then 1 minus 0.16, I'm just going to go ahead and put 8.84. Notice those two add up to 100. So that's those two numbers divided by 250. And then is less than P, and I'm going to move to the next line, is less than 0.16 plus 1.64 times the square root of 0.16, 0.84 over 250. Okay, so we've got all those pieces, and now it's just a matter of, can I successfully type it in my calculator? And I sure hope I can. Let's see if I'm successful. So I'm going to do 0.16 times 0.84, divide that number by 250, take the square root of it, and then multiply that by 1.64. And so I got 0.038 for that number. So I'll do 0.16 minus 0.038, and that's going to give me 0.122 on this side. 0.122 is less than P. And then on the other side, I will get the same answer. I'll do the exact same calculation, but with a plus sign in the middle here, and I'll get 0.198. So what does that mean? That means that I'm 90% confident that the actual number of people who approve of Congress is between 12.2% and 19.8%. So if people say, do individuals in America like Congress? Based on my study, it's between 12%, about 12% and about 20%. I'm 90% confident that the actual number of people like it is that range. Not very good, right? But it turns out this is actually pretty, like I said, pretty standard for Congress. Okay. Well, let's come over and look at 8.8 and read it. 8.8 says a medical researcher is trying to determine how the percentage of the population with genetic condition, and he sets out to create a 90% confidence interval with a certain proportion, and he wants to make sure that his interval is within 0.001 of the actual population. So what the researcher needs to do is he needs to take the error, and that error term is just this term from the binomial distribution. It's the part that we add and subtract from the average we take from our sample. So we have that our error term is ZC times the square root of p hat times 1 minus p hat over n. But the problem with doing this is we don't know what p hat is. So on part A, we use p equal to 0.5. So if you're not sure about what to do with these problems, you set the average equal to 50%. And in part B, the researcher has a little bit better approximation, so he used p equal to 0.02 and solves the problem. What do we do? Well, what we do is we put the error from the problem right here. We put ZC from the problem, which would be that 1.64 we calculate, and then we put our P in both of those places. And then you do a bunch of algebra, and solve for N. I decided that this is a problem that can be cut, so I'm not going to do 8.8. And there's one problem on the homework that is similar to that, and it's 8.3 number 9, so you can skip that problem. So this one problem, this one example, and this one problem you can skip, but you need to know how to make confidence intervals, you need to know how to do the rest of the homework problems, and you need to know how to do problems like 8.7. All right, so what we're going to do is next time we're going to do section 9.3, which is where we learn how to test these hypotheses. We learn how to do hypothesis tests with binomial distributions.